I have the top piece of plastic, Dave?
Here you are.
Thanks.
Here's a photomultiplier.
Is that clear enough?
Oh yeah, I can see through it nicely. One of the most startling predictions of the theory of special relativity is that moving clocks run slow by a factor, the square root of 1 minus v squared over c squared. Where v is the speed of the clock relative to the observer and c is the speed of light. For example, if we had three identical clocks at rest with respect to an observer, and at one moment they read the same, then of course we expect at a somewhat later time they will all read the same again. But if we have the same three identical clocks, but one of them is in motion with respect to the observer, then at the later time, let's say when this one has passed the others, it will read a lesser elapsed time, a shorter elapsed time than the ones that are at rest. As read by the observer, the moving clock runs slow. This effect is called the Einstein time dilation, and ordinarily it's a mighty small effect because v over c for most things is a very small number, so that this whole expression is very close to 1. For example, a clock moving by us in a rocket at 5 miles a second, it loses only 1 second in 100 years. But we do have some clocks that really go fast, that go 99% the speed of light, and they run at a ninth of the rate they do when they're at rest with respect to us. These clocks we're going to show you. These are mu-mesons, charged radioactive particles in the cosmic rays. First we have to detect them. So, detect mu-mesons. Then we'll stop some of these mu-mesons to measure the distribution of their radioactive decay times. As you'll see, this will enable us to use these mesons to measure time intervals. So, distribution of decay times used as clock. Finally, we'll use these meson decay clocks to measure time dilation. We'll compare two measurements of a time interval. The measurement by mesons going at high speeds with respect to us, and the measurement by mesons at rest with respect to us. The mu-mesons we'll use are produced high in the atmosphere and come shooting down toward the Earth. As they come down, some of them disintegrate in flight. The number arriving at a high altitude is greater than the number surviving to reach sea level. Right now, we're up on top of a mountain, Mount Washington in New Hampshire. We will count the number of mesons that arrive here, and then we'll go down later to sea level and count the number that survive to arrive there. By comparing these numbers, we will show that these moving clocks run slow. To start, we need to detect these mu-mesons.
Every time one of those mu-mesons, which Professor Frisch has told you about, passes through this special plastic scintillator, a flash of light is emitted. In fact, the plastic is scintillating right now from the mu-mesons that are passing through it. We can't see them because those flashes are much too dim to be photographed. So we detect them with this photomultiplier, which is just an extremely sensitive photocell, which turns the flashes of light into usable electrical signals. Of course, when working, we have to put the plastic up next to the photocell, like that. And then to keep out stray light, we have to cover it with a light-tight cover. First, this aluminum. That's shiny to reflect the light around inside. And then, finally, with this light-tight piece of cloth. Now I can turn on the high voltage to the photomultiplier. The electrical signal from the photomultiplier comes out in this cable, which I take and plug into this amplifier. I take the output of this amplifier and put it into the trigger of this high-speed oscilloscope. So every time a mu-meson goes through our plastic scintillator and is picked up by the photomultiplier, the electron beam of the oscilloscope starts moving and sweeps very rapidly across the scope face. We also take that same signal from the photomultiplier and put it on the vertical deflection plates of the oscilloscope so that the starting pulse is visible at the beginning of the trace. Most of these sweeps indicate the passage of a mu-meson clear through the scintillator. This spot is where the oscilloscope beam rests until a mu-meson enters the scintillator and starts the scope beam sweeping. The pulses that start the sweep are displayed over here. Notice that their heights vary. That's because some of the mesons go through just a corner of the scintillator, making a small flash of light, and hence a small signal, whereas others go all the way through. The sweep passes by each one of these major divisions in a microsecond. Right now, it's sweeping across 7.5 microseconds. Later, it will sweep across all 9 millionths of a second, which you can see. That may sound pretty fast, but one of our mesons enters the scintillator, passes clear through, and leaves in only about 2 billionths of a second, which is about 1/100th of the width of one of those starting pulses. So the width of the pulse has nothing to do with how long it takes our mesons to go through the plastic scintillator, but is determined entirely by the electronics.
Most of the mesons shoot right on through the scintillator. We can stop some of them in the scintillator, however, by slowing them down in this 2.5-foot thickness of iron. Incidentally, that's a big pile of iron. It weighs more than 10 tons. We want to stop some of the mu-mesons in the scintillator in order to observe their radioactive decay.
That brings us to our second point. We already know how to detect mu-mesons. Now we want to find out how long it takes them to decay, so as to use them as clocks. When a positive mu-meson decays, it gives off a neutrino, an antineutrino, and one positive charged particle called a positron. When the mu-meson enters our scintillator, it makes a flash of light. If it stops and decays in the scintillator, the positron makes a second flash of light. That puts a second pulse on our oscilloscope trace at the instant the mu-meson decays. So now we're ready to stop a lot more of these mu-mesons and measure the time distribution of their radioactive decays. So Dave, push the scintillator under the iron, and I'll get back to the scope. Let's have a look. You may notice that there are fewer sweeps than before. That's because the iron not only slows down the mesons, but it actually stops some before they can get to our scintillator. You also see that most of them still go all the way through, thus giving just one pulse. But there, did you see that one? About 2 divisions out from the starting pulse? Let's see some more. There. There. Now I want to look at the next one in a little more detail. There. That one still has the first pulse on it where the meson entered the scintillator. That meson had just the right speed to be slowed down by the iron so that it would stop in the scintillator. It then sat around for a while before it disintegrated, thus giving the second pulse when the positron was given out. The time it took the meson to stop was completely negligible on our scale. We can tell how long the meson sat around at rest in our scintillator before it blew up because we know that it takes just 2.9 microseconds for the beam to sweep from the starting pulse to the decay pulse. Now let's look at some more. There. There. You see that these pulses are occurring at different places across the face of our scope. And that indicates that the mesons take different lengths of time sitting around in our scintillator before they blow up. So if we're going to use these mesons as timing devices or clocks, we're going to have to accumulate quite a stack of data. To make data taking easy, I'm going to move the starting pulse over here to a predetermined position behind a mask on the scope face. And then I'm going to move the main trace up behind a second mask. Now, you will only be able to see the decay pulses. There. There. And there's another. These are the only pulses which we need to record. You saw the decay pulses peeking out from behind the mask. Here, let me show it to you. We're only interested in where those decay pulses occur on our time scale. And the easiest way to record that is to use this Polaroid camera. If we leave the shutter open, we can record up to about 20 separate events, one after the other, on a single exposure. We also have a photomultiplier, which looks through this aperture in the camera mount at the decay pulses. But before we can use it, I need to seal out the room light.
The light from the decay pulses that show out from behind the mask is picked up by this photomultiplier. Here's the high voltage input for the photomultiplier. This cable has the signal output from the photomultiplier. It comes up into this amplifier. It enters in the back here. The output comes out in the back here. Comes up to this circuit, which is actually a scaling circuit, which is just used as a driver for this register. This register counts individually the mu-mesons which have entered the scintillator, decayed, and their decay pulses have counted on the photomultiplier. If you're ready with the taping, Jim, I'll turn on the high voltage.
It's okay. Go ahead. I'll turn on the counter and open the camera shutter.
There's one. Remember, this counter gives a running record of the number of mu-mesons that have stopped and decayed in our scintillator. How about, should we take 5 or 10?
Oh, 5's enough, Dave.
I'll go over and get the chart ready.
Well, here's our picture. Let's take a look at it. Here you see the pulses which are counter-recorded, all 5 of them. The starting pulse is over here just behind the mask. Now what I want to do is to measure the length of time which each one of these mesons lived, so that Professor Frisch can plot it on his chart. There's a convenient ruler to use, simply another exposure of the grid on the scope face. Now I'm measuring from the edge of the mask, and I find that this particular meson lived for 4.85 microseconds.
4.85. I'm drawing on this expanded scale a line representing the length of the decay time of that meson in microseconds.
Now, Professor Frisch is plotting those times vertically downwards for a reason that will be obvious later. But I don't want you to think that that has anything to do with the distance from here to here. It has to do with this distance. The length of time the meson lived in the scintillator. Now here's another one. This one only lived for 0.65 microseconds.
0.65.
And this one, 2.90.
2.90 microseconds.
This one, 0.80.
0.80 microseconds.
And the last one, 3.45. Oh no, that's closer to 3.50.
Microseconds. Okay, here are the lines showing the decay times of these 5 mesons we got. We put them side by side just to display them together, but this coordinate doesn't mean anything. It's only the time which we plotted in that direction that means something. In order to see the pattern of the distribution of the decay times, we will need to take many hundreds of counts. So, Jim, would you start an hour's run? You got film in the camera?
Yes, there's only one going. You see our first counts coming in. To show you a complete hour, we will compress time so that you will see it in the next 25 seconds. Also, we'll show you samples of the Polaroids, which we took during the hour. $568. 2.40.
Okay.
2, 3,
Okay.
1.65.
3.60.
2, 3, 4.
Okay.
1.6. Okay, here's another one.
Okay.
1.65. 8 per second.
0.85.
Okay, here's.
Okay.
So here's our finished chart, based on the 568 counts which we got during the hour.
The 568 counts we had plotted on our chart are the result of 1 hour's run. Previously, we had taken 5 different runs, each for an hour, and their average comes out 564, so that the 568 we have plotted are indeed a good sample of the number of mesons decaying in our scintillator every hour.
So you can think of the mu-mesons as coming down in a steady rain from hour to hour. Many mesons live for as long as 1 microsecond. Fewer live for 2 microseconds. By the time we get to 5 microseconds, only a small fraction of the original number remain. And by the time we get down to 8.5 microseconds, which is the longest time we can see on the scope face, only a very few mesons are decaying.
That chart is a pictorial representation of the decay times of those mesons which had stopped in the scintillator before we began to measure their decay times. They were at rest with respect to us during the time shown on the chart. Now we come to the heart of the experiment. What happens to the decay times of these mu-mesons when, instead of being at rest with respect to us, they're shooting on down by us with speeds nearly that of light? Let's look at the chart in more detail.
For instance, here's a meson which lived for 3.5 microseconds sitting in our scintillator. Suppose we hadn't stopped it. Where would it have gone? Here we are, up on top of Mount Washington, 6,300 feet above sea level. We stopped that meson up here. If we hadn't, it would have gone on for 3.5 microseconds down below before decaying. Now how far would that have been? It would have gone a distance 3.5 times 10 to the minus 6 seconds times its speed v. So in order to know just how far it would have gone before decaying, we need to know its speed v.
Fortunately, we do know the speed of the mesons which stop in our scintillator because we know how far a charged particle of a given mass and speed can go through matter. A mu-meson entering the top of the iron with 0.9950 times the speed of light gets just into the top of the scintillator before it stops. With any less than 0.9950 C, it stops in the iron. With slightly greater, 0.9954 C, it goes down and stops in the bottom of the scintillator. With greater speed than that, it goes on through